Hello everyone. We are starting our first chapter in Astro 3. I hope that you all have the text. And my job is to explain the tough stuff to you. So I don't go over the easy stuff. And I give it some more context than you might get in the book. In this first chapter, I want you to concentrate on the observations rather than on the explanations. We get to the explanations later when we understand more about the observations. So let's go for it now. And when we talk about this chapter, we're talking about where we are in the universe. That's what we're going to spend a lot of time on, and your place in it. I want you to know that above my staircase leading down from my second floor, I have a placard for my sons. And the placard says, "Shoot for the moon. Even if you miss, you'll land in the stars." So I am always thinking about our place in the universe, and I want you to think that way too. And keep that in mind. Shoot for the moon. The second part of what we're going to talk about is when is now. We'll get there, but we have a lot to do to understand where we are in the universe first. And we always start with what you know and we build on it. So this is really elementary stuff, and don't worry, we're going to get complicated later on. When we talk about how big the solar system is, I want to start with something that you know. And probably many of you have heard of the Air and Space Museum. Probably some of you have been to the Air and Space Museum, so I wanted to relate it to that. In front of the Air and Space Museum, there is what's called the Voyage Scale Model System. And that is a scale model that looks at a grapefruit-sized sun and then takes it on a 1 to 10 billion scale. And our whole point here in learning about where we are in the universe is to talk about scale. So if I tell you that the sun as a grapefruit is a 1 to 10 billion scale, in other words, the sun is 10 billion times bigger than a grapefruit, then you can get an idea that the Earth in this scale is the size of a ballpoint in a pen. All right, so it's right here, this letter I with the dot above it. It's the size of this Earth in this model system in front of the Air and Space Museum. And so what I wanted to point out to you is right in front of the Air and Space Museum, they have the grapefruit for the sun. And then all the way down at the Smithsonian Castle, past 7th Street, toward the Washington Monument, 600 meters away, is Pluto, which is not even a planet now, but we'll get to that later. So I wanted you to have an idea that when you have a grapefruit-sized sun, 600 meters, which is going to take you longer than 2 minutes to run if you are a really fast runner, is what you will find for where the outer limits of our solar system is. Now that gives you an idea of what we're talking about, and I mentioned that Pluto's no longer a planet. So how far is the nearest star? Because we just talked about our solar system, and our sun is our star. So how far is the nearest star outside of our solar system? Well, if you had that grapefruit in DC over here, then the nearest star is actually Alpha Centauri, which is near the Southern Cross, which is in the southern hemisphere. You're not going to see this. But that star would be another grapefruit all the way in San Francisco. So that's a long way to go to find the nearest star. And that gives you some idea of scale in a big sense before we get down to applying these observations that we know about via telescopes. Now we take those observations and we apply some math to it. Don't freak out, you can do this. So when we apply some math to it, let's look at multiplying your seen by 100 times. Right? We can do that. It's the easy stuff first, the stuff you know. You see a park bench here. You see a sidewalk here, some trees. This is about 16 meters, about 52 feet in a park. You could do that. That's probably from a drone. If you take that and magnify that view, that field of view that we're applying math to, we can actually see a big town that's associated with that. That's a pretty big town right there. There's an oval track probably around a high school. So you can see this is probably about the size of Morristown, right? If you took Morristown and expanded the view 100 times, you would get the Susquehanna River, all right? There is the Delaware River coming in through there. This is all around the Chesapeake Bay. This is the region on Earth, all right? Let's keep going. These are things you know. If you took that regional look from a satellite and blew it out 100 times, you'd be looking at the Earth in space, all right? And that is about 100,000 times over the park bench. If you exploded that 100 more times to 10 million times the park bench, you would see the Earth and the moon orbiting it and quite a bit around it, all right? And if you took that view and multiplied it 100 times the park bench again, you would have 1 million times the park bench. And you would have a new unit, because this is getting all pretty unwieldy here. And this new unit is something we're going to talk about. It is basically the distance from the sun to the Earth. We'll talk about it in a second. Let's go back to the basics of what you know. All right, what is a planet? We just looked at the Earth there. But what is a planet? A planet is a non-luminous body. That means that there's no light put out by the planet. Instead, the planet reflects sunlight. That's a planet. It reflects sunlight. Non-luminous from the Latin for lumen, light. What is a moon? A moon is an object or a satellite, better word for it, an object or a satellite that orbits a planet. Interestingly, the word moon is derived from Old English for month, as opposed to month, because the phases of the moon go by in roughly a month, and that's related to Latin for menses. All right, so I think that makes a lot of sense. I am giving you this etymology because I'm trying to stress how long we have been studying the sky, back to the Greeks and the Romans, back much further than that. What is it to orbit? We talked about the moon orbiting the Earth here. The verb to orbit means to travel in a circular or elliptical path around a central body. Now that central body, if we talk about the Earth orbits its axis, straight down through the middle. The Earth also orbits a central body of the sun. All right. The moon orbits the central body of the Earth. Our solar system orbits the central body of the Milky Way galaxy. So it's all about what the central body is when we talk about orbiting. From the Latin word orbita, which is a course. Orbit, course, you see how those might go together, or a wheeled track around. We're going to be talking quite a bit about ellipses, but not right now. We'll get into a little bit now. What is an ellipse? An ellipse is basically a cross-section of a cone. It could be a cross-section in just about any way. If you took a cross-section right off the bottom of a cone, you'd have a circle, and a circle is an ellipse. If you took a cross-section on a high angle, you'd have quite an oval, and an oval is an ellipse. We're going to be talking about this quite a bit. It's from the Greek word, because this was studied long ago, for ellipsis, meaning alleviating a deficit. If I took a cross-section out of a cone, I'd be taking something and making it leave. An ellipse. All right? Now, not to be confused with an eclipse, which is actually from the same root. And that root has, in addition to it, the ec, is from ex, meaning out. And what they're saying is an eclipse, as you know it, is a cone shadow over the earth, sometimes over the moon. We'll talk about this quite a bit. A cone shadow that leaves out light. So the same leaving, the same cone, we're talking about light here. We also talked about our star when we talked about distances. Well, what is a star? A star is a glowing ball of gas that generates its own heat and light, as opposed to a planet, through nuclear fusion in its core. Much more about this later, just going over the basics. From I'm sorry, I should change that there. Star is from the Latin for stella. I'll change that on the PDF. See you on the other side.